Hello everyone. Today in this session we are going to see last two types of passive devices which are used in the microwave communication circuits. These are ferrite devices called as isolator and gyrator. So let's first look at what is isolator and what is it the use of such isolator. So a microwave isolator is nothing but a non-reciprocal transmission device. Now, non-reciprocal means it will work in one direction and it will not work in the opposite direction. So, such device is used to isolate one component from reflections of other components in the transmission line. So, when waves are transmitted from a transmitter, due to presence of different components within the waveguide or within the transmission line, some part of these waves are reflected back. Now these reflected waves causes problems in the transmission of the original waveform. The whatever wave we get at the end of the waveguide, that is at the load, is degraded in quality because of these reflections. So these reflections impact on the quality of wave received at the load or obtained at the load. So it may be degradation in power, it may be change in the phase angle of the transmitted wave and several other parameters also. So in order to avoid this, whatever we wanted to transmit, in order to obtain it as it is without any attenuation or without any changes in original form, we have to use isolator. So the ideal isolator completely absorbs the power for propagation in one direction and provides lossless transmission in the opposite direction. So that's why it is non-reciprocal. So if we are transmitting in this direction, the transmission should happen without attenuation, no absorption of power, and transmission in the reverse direction, that is reflected wave, should completely be absorbed. So it works only in one direction, and that's why the isolator is usually called as uniline. Uni means one, line means direction. In one direction it also only works. So isolators are generally used to improve the frequency stability of microwave generators. So because of no reflection, the stability of frequency can be achieved. The devices such as klystrons, magnetrons, which we will see in the next module, these use the isolator in which reflection from the load affects generating frequency. So in klystrons or magnetrons, if we get reflections, then whatever frequency we want to generate, it will be affected because of this reflection. So to avoid that, isolators are usually used. So in such cases, isolators are placed between generator and the load. So let's say this is a microwave generator. That means it may be oscillator, it may be any other thing. And its output is obtained at a load impedance here. Now between this, there may be other devices also. So there should not be any reflection from here. One simple way is providing a matched load, because matched loads will transfer maximum power from the circuit towards the load. So matched load avoids the reflection. So that is one way, but there can be separate device that can be used for isolating reflected waves from original wave. So as a result, this isolator maintains a stability of the frequency of the generator. Okay. So there are several ways in which isolators can be constructed. One we have just discussed, that is use of a matched load, which avoids any kind of reflection, because if load is matched, that means output impedance of a circuit is matched with the load impedance of the circuit. This is RL or ZL, I can say. This is ZL and this is Z0. Then if Z0 is equal to ZL, then this is a matched condition, and because of this there will not be any reflection and there will be isolation. So they can be made by terminating ports 3 and 4 of a 4-port circulator with matched loads. So 4-port circulator we have already seen in the last previous sessions. So you can use matched load to provide isolation. On the other hand, a special devices called as ferrite devices can be used. For example, a ferrite rod can be used along the axis of rectangular waveguide, as we are going to see in the next slide, that is the schematic of that rectangular waveguide with the ferrite rod. The isolator which we are going to see is a Faraday rotation isolator. We have seen previous types of this Faraday rotation also. Faraday rotation is a principle on which this isolator work. So we have seen Faraday rotation, phase shifter, we have seen a circulator regarding that. So let's see what is isolator. Now if you see, the diagram is similar to the previous one. The first part, that is this is rectangular waveguide. This is also rectangular waveguide, or we are calling it as a rectangular to circular transition, or circular to rectangular transition in this case, and the middle part is a circular waveguide. Okay, so same concept is used over here. Now what we are doing here, input waveguide it is, that means we are applying the input wave here which will enter in a rectangular to circular transition. Inside that waveguide we are placing a resistive card which is made up of ferrite material. It is placed parallel to the direction of propagation. Now if wave is parallel to the wave is along a z axis, that means electric field will be onto the x axis. So this is wave traveling z axis, this is electric field along the x axis, and magnetic field on the h axis. So this resistive card, if we are considering rectangular waveguide, then it will be TE10 mode, that will be dominant one. Now when it enters into the circular waveguide, that is the middle part, here TE10 mode will be transformed into TE11 mode, which is a dominant mode for circular waveguide. That is because of polarization which is caused by Faraday rotation. Now the rod inserted here is a rotated ferrite rod which is rotated by a magnetic field. How much it is rotated we will see later on. Once the wave comes out of this one, it enters into circular to rectangular transition waveguide, where another resistive card here is placed which is at 45 angles, you can see 45-degree angles to the original position of the resistive card in the first waveguide or input waveguide. So the phase shift between these two, or difference in angle between these two, is a 45-degree. Why this is done, again we will see. And finally the output is obtained in the output waveguide. So how does this isolate the forward going waves from the reflected waves? As you can see in this particular diagram, the reflected waves are kept within this particular part of the construction. So this resistive card reflect waves in this direction and they remain within this. So whatever input we have given here, same output will get here, because reflections will stay within this part. Okay, so how it is done, let's see that. The input resistive card is in YZ plane and the output resistive card is displaced 45-degree with respect to the input card. So if input card is this, output card will be 45-degree angle to that particular input card. The DC magnetic field which is applied longitudinally, that means along Z direction, to the ferrite rod rotates the wave plane of polarization by 45-degree. Okay, this rod which is placed in the middle will rotate the polarization of wave by 45-degree, because rod is rotating because of presence of DC magnetic field. Okay, now the degree of rotation, why 45-degree? The degree of rotation is always dependent on length and diameter of the rod. So if you want a different amount of rotation, you have to change the length and diameter of the rod. And apart from that, what is the DC magnetic which is applied to that particular rod, because rod will only rotate in the presence of DC magnetic field. If we don't apply DC magnetic field, and even if we apply the input signal, then rotation will not be possible for the rod. Okay, an input TE10 dominant mode is incident onto the left end of the isolator, that is at the input side. Since TE10 mode wave is perpendicular to the input resistive card, that means E is perpendicular to Z axis because input resistive card is along the Z axis. The wave passes through the ferrite rod without attenuation. As E is a perpendicular, let's go back. So this E is traveling here, no attenuation, and it will go through this one even if there is a change of mode because of rectangular to circular transition, because E is always perpendicular to the H. Okay, now in this direction it is traveling without any attenuation. What happens next? It becomes now TE11 mode. The wave in the ferrite rod section is rotated clockwise by 45 degree because the rod is rotated 45 degree. So wave also gets rotated by 45 degree and it becomes normal to the output resistive card. Now since wave is also rotated, that E vector electric field will also rotated by 45 degree. Okay, and it remains normal to the output resistive card. Okay, and that's why the output resistive card is kept 45 degree angle, because when we are transitioning from circular to rectangular waveguide, then again the rotation will happen, that is polarization of input wavelength, and that's why the card has to be at the angle, because rotated wave has to be absorbed now in the reverse direction. Okay, so let's see what happens next. So as a result of this rotation, the wave arrives at the output end without attenuation. Now electric field is still normal to the output resistive card, so it will not attenuate anything and it will allow to pass it through, and output is obtained without any attenuation at the output waveguide. In the reverse direction, let's discuss how reflected waves are absorbed. A reflected wave from output end is similarly rotated clockwise 45 degree by the ferrite rod. Now the wave which are reflected, now it will come towards the ferrite rod here. Now these are 45 degree angled to the ferrite rod. Now this actually there should be, this electric field should be in the x direction in order to pass through, but since it is at an angle of 45 degree, it will be absorbed by the ferrite rod. Okay, because during this transition wave was polarized, and that's why it will come back in a polarized manner and will be absorbed by the ferrite rod. However, since the reflective wave is parallel to the input resistive card, now once we get back from this rod to the now input resistive card, now let's see back again. We have seen what happens when wave reflected from here. Rod will absorb everything. Now if waves are reflected from here, what will happen? They are further rotated by 45 degree, so they will be parallel to the input resistive card. So it will go back in this direction and parallel to the input resistive card, and they will be further absorbed by the input resistive card. That's what it is said. So if a reflection occurs before the rod, it will be absorbed by the input resistive card. So that's what it is said. Since the reflected wave is parallel to the input resistive card, the wave is thereby absorbed by the input card. So absorption is done by input resistive card and the ferrite magnetic rod. So in this way, first two rods, ferrite rods or ferrite devices, will absorb in the reverse direction and allow the transmission in the forward direction. So this is the ideal working, but the typical or practical performance of this isolator is about 1 dB insertion loss in forward transmission. We have said that waves travel in forward direction without attenuation, but that is the ideal case. So practically 1 dB loss is observed, but it is very low, so it is acceptable. And in the reverse direction, the loss achieved is a 20 to 30 dB, so that is a good isolation in the reverse direction. Okay, so isolators play important role in achieving a good quality output at the load. Okay, now what if we don't want to use a ferrite rod? Is there any other way apart from Faraday rotation that we can provide attenuation in other direction and transmission in one direction? For that, a separate device is used that is called as a gyrator. So another important canonical non-reciprocal component is gyrator, which is also type of a two-port device having a 180 degree differential phase shift. Now because of this 180 degree differential phase shift, forward wave and reverse wave will cancel each other and absorption will be obtained. Now generally this gyrator is considered as a fifth element, basic element in the construction of electronic circuit. Fifth means which are the first four: resistors, capacitors, inductors, transformers. These are four basic elements, and to add to that, a gyrator is considered as a fifth element which acts as a very important device in case of isolators and circulators. The schematic symbol for gyrator is shown in figure, which is this one. So it's a simple block shown with pi indicating 180 degree phase shift in one direction. That means it will be allowing in this direction and absorbing in opposite direction. Okay, and its scattering matrix, obviously transmission reflection coefficients will be 0 because of absorption, so diagonal elements are 0, and transmission coefficients are equal in magnitude but opposite in polarity. Okay, that is the S matrix. So S matrix shows that it is lossless because of 0 reflection coefficients. It is matched because transmission coefficients are of equal magnitude, and non-reciprocal. Non-reciprocal because magnitude is same but polarity is different. Okay, so use of gyrator is a basic non-reciprocal building block in combination with dividers and couplers can lead to a useful equivalent circuit for isolators and circulators. So in the isolators or even in the 4-port circulator, you can use a gyrator to provide the desired phase shift and isolate the reflected waves from the transmitted waves. Okay, so let's see the example of this gyrator. An isolator constructed with a gyrator rather than previous resistive cards which we have seen in the 4-port isolators and 4-port circulators. So a gyrator and two quadrature hybrids are shown in figure. So these are quadrature hybrids which are a part of our microwave communication circuit, which don't want any kind of absorption of a power in one direction. So the forward wave is passed. So in this particular case, this wave will be passed and this wave will be absorbed, or in this case this wave will be passed and this wave will be absorbed. Okay, so forward direction it will be passed, in the reverse direction everything will be absorbed, and considering as a match load of the first hybrid. The gyrator can be implemented as a phase shifter also because it provides a 180 degree phase shift. A bias can be provided with a permanent magnet. Because of presence of magnet, electric field will be generated that can provide a bias potential, making a gyrator a passive device. So gyrator is not actively generating anything, it is just acting as a transmitter in one direction and attenuator in the other direction. Okay, so this is another type of device which is popularly used in the microwave communication circuits. So this marks the end of the second module, in which we have seen several passive devices which are used in the microwave communication circuits, such as attenuators, phase shifters, isolators, circulators, and then gyrator. Just now we have seen. From the next session we will see the tubes which are used in the microwave communication circuit and why they are used in those circuits. That's all for today. Thank you.